My name's Jim Weirich. I'm the real Jim Weirich, in case you were confused. It's really exciting to be here tonight. It's a real challenge, I found, to condense about a 45 or 60-minute talk into 30 minutes. So we might go a little bit fast, but I think it's going to be fun. I want to start off by saying that I'm the chief scientist for EdgeCase, and one of the things I do for EdgeCase and for clients is to do technical interviews with people that they might want to hire. And generally they're phone interviews, and they take anywhere from half an hour to an hour long. And I just want to have a good technical conversation with whoever it is to kind of gauge their skills on different topics. And there's a number of questions that I typically ask when I'm doing a technical interview. One of them is, what technical books have you read recently? And this is to kind of gauge how they approach learning and if they're interested in continuing the learning process even after they're out of school. And one of the answers I get quite often is this book. Thank you, James. Another question I ask is, what do you look for in a good design? In other words, if someone laid a program down in front of you and you were doing a design review on this program, what are the things that you look for in a program to know if you're doing a good design or not? And sometimes I get good answers. Sometimes I get kind of this blank silence on the end of the phone. And it's kind of and they can't articulate it. They might be able to have a gut level reaction to whether a design is good or not, but a lot of people find it hard to articulate what goes into a good design. Let me just throw that question out to you. If you're looking at a program, what are clues to you of a good design?
Simplicity.
Simplicity, okay?
Short methods.
Short methods.
Specs.
Specs and tests, okay?
It's easy to explain to somebody.
Ah, okay. The telephone test. Can you explain it over a telephone?
Does it accomplish its goal?
Does it accomplish its goals, okay? Yes, in the back.
Is it extendable?
Extendable. Okay.
Easy to do common things?
Does
Easy to do common things.
easy to do common things. Okay, yes, clear in the back.
How comprehensible it is, how quickly can you comprehend it? That's to me the...
How comprehensible is it? Readability, yes.
It's just have symmetry.
Consistency down here, what was up there?
Does it act the way that people would expect that it would act?
Okay.
Encapsulation.
Encapsulation, yes, fellow with the hand.
WTFs per minute.
The only true code metric, WTFs per minute. Well, this is great, this is great. When you go to a conference, you are expecting the people who want to learn, and you guys have lots of ideas, and I really love this. And I've been doing a lot of thinking about design principles lately, and I've been kind of looking for a way to kind of put all these things together under one hat. Someone said that they would come and listen to me talk about oatmeal. So we're going to talk a little bit about oatmeal. Let's wind back clear to the beginning of the 1900s. And at that time, scientists, physicists felt that they had a pretty good understanding of the world around them, that there were only a few open questions left in how the world was put together. And that the physicists would be obsolete in the 20th century because they figured everything out. And there was an experiment done by Ernest Rutherford who took a gold foil and hammered it down to be only a few atoms thick. And at that time, the belief about matter was that matter was a lot like a bowl of oatmeal, that it was consistent all the way through, that there was no, it might be just a little bit lumpy, but there were no hard surfaces in it at all. So he took this gold foil and shot alpha radiation through the foil, and then measured how far the alpha particles were deflected from a true straight line. And if matter was truly a bowl of oatmeal, that'd be like shooting a bullet through the oatmeal, and it should go through more or less. It might deviate a little bit, but most of them will go through. And he found that for most of the alpha particles going through his thin gold foil, that was absolutely true. But in about 1 out of every 8,000 particles deviated up to 90 degrees. Some of them even reflected straight back towards the particle emitter. And if matter was truly a bowl of oatmeal, there was no way he could explain this bizarre behavior of matter being reflected back. It turned out matter is not a bowl of oatmeal, but it's oatmeal with raisins in it. And this led to the whole theory of atomic theory, where the atom is a nucleus, a small nucleus, in a mostly open atomic structure with an electron cloud floating around it. And we began to understand the internals of how atoms were put together. And physicists discovered that there were about 4 basic forces in the universe. There was the force of gravity, which we have understood for years. Turns out the force of gravity, even though it is the major force over large interstellar reaches, it's actually the weakest force that we come in contact with. There's electromagnetism, which, interestingly, there used to be electric fields and magnetic fields, and Maxwell put together the two into an electromagnetic field and found one theory that combined the two forces into one. There was the strong nuclear force, which holds the quarks together inside the nucleus, and then there's the weak nuclear force, which controls the decay of neutrons into beta particles. And those 4 forces are what the scientists discovered, and as far as they can tell, those are the 4 forces there are in the universe. Now, this puzzles scientists because, just like in computing, there's only 3 numbers, 0, 1, and many. And there was no reason they could think of why there should be 4 different fields instead of 1 field. And so they would love to come to a theory, just like they united magnetism and electric fields, they would love to come up with some kind of grand unified field theory that would explain all the fields. And they've discovered, at least so far, that under high energy conditions, at least some of the fields, like the weak nuclear force and electromagnetism, kind of tend to merge together, and they're really special cases of a single field. But they're still looking for that theory that will explain everything. In software, we're kind of at that same place today. We have a lot of principles that we use to write good software. The solid principles, these are from Bob Martin, and single responsibility, thank you. Single responsibility, open-close principles, Liskov substitution, interface, inside out. Not inversion, dependency inversion. No, that's, yeah. Dependency, D is dependency inversion, interface segregation is I. So we've got a bunch of principles there. The law of Demeter is a principle that a lot of people follow. The dry principle we're all familiar with, keep it simple, don't repeat yourself. Writing small methods, someone over here called that one out. Designed by contract. So there's a lot of principles involved, but is there kind of one kind of grand unified theory of software development? And that's kind of what I've been thinking about here recently. So the title of my talk is really the grand unified theory of software development, and I want to talk a little bit about that. So let's go back in time to the beginning of my career. I was just out of college and I was working at NASA writing Fortran programs down there to manipulate radar data. And my mentor, everybody should have a mentor when they first start out. He gave me this book and said, read this book, this is important stuff. And it's a book by Glenford Myers called Composite Structure Design. Now if you're familiar with the times, structured design was the big thing back then. And we just figured out that we don't need to use go-tos, that everything can be expressed in while loops and if-then-elses, and that was the big controversy of the day. No one was worried about strongly typed or weakly typed languages. It was whether it was structured or not. So structured design actually is more about design rather than coding, but since structured was kind of the catch-all thing, the book was named for this. And one of the things I really remember well out of this book is its chapter on coupling and cohesion. Now, cohesion is how well a single module fits together. Well, coupling is the connections between modules. And Glenford Myers said that there are 7 different types of coupling. And he arranged them from the very high coupling, the bottom here, content coupling, which is bad, to no coupling, which is good. Just let's explain these things just real briefly here. No coupling is pretty obvious. If 2 modules are entirely independent of each other, there's no coupling between them. Content coupling is where one module reaches into the insides of another module and messes around with it, bypassing its private, bypassing the API, just reaching in and munging on it. That's the worst kind. Don't do that. The 4 here kind of centered have to do with data and how it's passed between modules. So the top 2 are local data. The data is local to the 2 modules. The bottom 2 is global data. Data is global to everybody. And then they are further differentiated by whether they are simple data types or structured data. So local data coupling would be passing integers or floats or strings into a method. That'd be all local data, simple data structures. Stamped coupling would be passing structures, things that have form, internal structure, and passing them through a parameter. Control coupling in the middle. This is an interesting one. This has to do with the calling sequence on a method. And if a method has a flag parameter and that flag controls the algorithm that the method is going to use, then it's control coupling. And symptoms of this is if you describe the function and you have to use the word or in the description, or something semantically equivalent to or. And also the flag value is arbitrary. It has a meaning, but you could change the meaning and there's no real difference in what it means. If it's an arbitrary value, then this is probably control coupling. And control coupling falls right in the middle of bad things. Not super bad, but not super good either. And truth is, we see a lot of control coupling in the code we look at today. For instance, instance methods. What does this method do? Returns a list of methods on your object. Well, maybe. Depends on how you call it. You can pass it a true flag or a false flag. One of these methods returns all the instance methods. The other one returns just the instance methods in that direct class. Now quick, which one's which?
True is direct class.
True is direct class. How do you remember that?
That's the only one I use.
It's the only one he uses. There's no reason why true should mean that as opposed to false. So the value of that flag is arbitrary, and it controls the algorithm. In fact, if you look at the description has the word otherwise right in the middle of it, which I will claim is semantically equivalent to or. So control coupling. Other examples of control coupling. The finders in Rails are control coupled by the first parameter, whether it's a first symbol or an all symbol. And the way we can really tell this is the fact that they return 2 different kinds of things. The first one returns a single object. The second one returns a list of objects. So there's never a case where you would pass in that first parameter that could vary between the 2 values, because you'd have to handle the output different. So this is another case of control coupling. So that was back in the 70s. And Myers classifications were good, but they had a major problem in that it didn't extend well to object-oriented languages and not to dynamic languages either. So it was good at explaining software of that period, but in today's dynamic OO languages, we need something a little more, something that gives us a little more information. So, fast forward to the late 90s. There was a book by a fellow named Mealer Page Jones called what every programmer should know about object-oriented design. Now, despite the fact I have used titles like this in my talks, this is a rather pretentious title. And the book itself is divided into 3 parts. The first part is an introduction to object-oriented design, and it's okay if you've never seen OO before. It's a good introduction. If you have seen it, it's not going to tell you anything new. The second part of the book is an introduction to a graphical notation for describing OO designs. No one uses that particular notation, and in fact, several years after this was written, everybody switched to UML and started using UML to describe designs. So the second part of the book is not really worth it either. However, the third part of the book is worth the price of the entire book. And in that third part, he defines a term called connascence. And connascence is defined to mean things that are born together and change together. Particular, for software, connascence means that 2 pieces of software have a connascence relationship if changing one makes you change the other. So software has a connascence relationship if changing one makes you change the other. They have a coupling, in other words. And rather than the 7 layers of coupling that Myers talks about, Miller-Page-Jones defines connascence in very operational terms. And he talks about different kinds of connascence. And for the rest of the time here, I'm going to talk about a few of those different kinds of connascence. And as I was relating the different kinds of connascence to a friend of mine that I work with, he says, this is great. You can explain this principle with that and that principle. So he's the one who kind of gave me the idea for the grand unified theory of software development. So let's talk about the first connascence principle. We have a model object called customer. It has a method on it called email. We also have somewhere else in the program, we have a method called sendMail that takes a customer and sends something to the customer via his email address, and we use that. There is a connascence between these 2 pieces of software, related by the name of the method, email. If I change the name of the method email in the model object, I have to change it in the client object as well. So there's a connascence between them, and we call that connascence of name, because they are related through a name. Okay. Connascence doesn't have to just exist between software. It can also exist between a method and the database, because this ties back to a column named email into the database. So changing the name in the database necessitates a change, possibly a change in our software as well. So connascence of name between 2 pieces of software. Let's see, is there another example of connascence in this example? Okay, the customer class, the class customer and the variable name. Is this an example of connascence of name? No. Not really, because if I change the name of the class, it really doesn't affect the name used here locally. Now, semantically, there might be some mismatch, but it doesn't break the program in any way. So if there is any connascence at all, it's even weaker than connascence of name. So I would say this would not be an example of connascence of name. However, customer here. The first line has customer as a parameter. The second line uses customer within the method. So even between lines of a method, you have connascence. So connascence exists not only across modules, but within modules as well. It turns out that locality matters when dealing with matters of connascence. Within a module, or within a method, within a class, we tend to have a very strong sense of connascence tying the whole thing together. In fact, that's probably a good class design if things that are tightly bound by some kind of connascence are all put together in the same place. That means if one changes, the other changes, but they're in the same place so they can change together more easily. Things that are farther away, things that are away from, in a different module, in a different directory, in a different library, should have weaker forms of connascences connecting them. So that leaves us with the rule that as the distance between software elements increases, we should be preferring to use weaker forms of connascences, the rule of locality. Okay. Next, connascences principle. A while back, I was working on a web page that had orders listed on them. And the params hash that I got back looked something like this. It was a hash of order IDs with a value that came from a checkbox. And the value indicated whether the order should be expedited or not. And in the controller, I didn't want to deal with the ones, the one and the two. I wanted to deal with, should I expedite it? And I wanted to deal with objects, not order IDs. I wanted to deal with the orders themselves. So I translated that hash into a list of pairs. And each pair had a first element and a second element. The first element was the order, and I used the value returned from the params hash to find it. And then I translated the 1 and 2 into true and false, whether we should expedite or not expedite. So there is a connascence between the ordering of the pairs and the processing of this list of orders, this list of order pairs. In fact, if we compare the code that generated the list with the code that processed the list, it's easy to tell that if I change the order and the flag, their position, I'd have to change the code that processes that as well. Now this is a connascence, and it's not named because there's no names used between these. This is what's called connascence of position, where the position of an element within some kind of data structure, if you would change that, necessitates changing code elsewhere. Connascence of position. Okay. So, I wasn't too bothered by this particular connascence of position. It only had two elements. They were either in this order or that order, and there seemed to be kind of a natural ordering that you want the order object first and then the flag. However, if there was more information that I needed to process, what if instead of just two elements, I had the order itself, the expedite flag, a confirmation number, an order date, an expiration date, and maybe a special handling flag? All of a sudden, connascence of position becomes much more difficult to deal with. And if I was faced with this kind of thing, I would probably, instead of using an ordered pair, I would switch to some kind of data structure, like a struct or an o-struct, or maybe even a class with attributes, where I give each item a name, expedite, confirmation, order date. I give them individual names, and now the order within that object is no longer important because they are now identified by name. Essentially what I've done, I've taken connascence of position and translated it to connascence of name. Which in this case, if there were a lot of fields, I prefer the connascence of name over the connascence of position. That leads me to believe that degree is important. You can have a kind of connascence coupling going on, but the more of it you have, the worse it is. So also I will claim that connascence of name is better than connascence of position, because names won't change as often as position could. The position could change for any reason whatsoever. The name, probably not so much as long as I pick good non-arbitrary names. So connascence of name is a weaker form of coupling than connascence of position. And that introduces us to the rule of degree, which says that if you have a high degree of connascence, it's probably a good idea to convert it to a weaker form of connascence, as we did in our example, converting it from position to name. Okay. Another position example. Here we have a finder method that takes two arguments, a conditions and an ordered by. And when we call it, we have to pass in it parameters in a particular order. Turns out that Ruby methods have connascence of position every time you use a traditional list of arguments. It doesn't bother us if we have 1, or 2 parameters. But again, as soon as we increase the number of parameters, the connascence of position becomes kind of bothersome. Here we have all kinds of parameters being passed in, and when you need to do something like this, you want to convert it from connascence of position to connascence of name. And that's exactly what Rails did. They used a hash to identify the individual parameters, and we now identify the parameters by the tag in the hash rather than its position in an argument list. Conversion of connascence of name to a connascence of position when the degree got too unbearable. So that seems to be a good principle. Another example of connascence of position is a little oddball. This caught me last year sometime. We had a bunch of unit tests that went and grabbed an arbitrary user from our fixture data. Well, fixtures are bad anyways, but despite that, this worked great until we introduced the concept of roles into our users, that certain users were allowed to do certain things that others weren't. And it turned out that the first user in my test database was a different user than the user in his test database. So it would pass on my system and fail on his system. So we had randomly failing tests depending upon what user we happened to fetch from the database. This is connascence of position, where the position of that user returned from the database was important. Again, converting that to connascence of name was the solution to that. Find the user you want and return that exactly. Okay, another kind of connascence. One of the programs I work on is a medication giving program where you hand out medications. You have to check whether the medication was given, a green checkbox, or not given, or you're skipping it for this particular time period. So there's 3 values in there. The value you get back from the form is either a 1 or a 2, depending on whether it's checked given or checked not given. That means that the code actually has to check to see, is this a 1, and if so, mark it given. Is this a 2, mark it not given. What we have here is connascence of meaning. The individual variables, 1 or 2, have a meaning assigned to them above and beyond what a 1 or 2 mean. I mean, 1 and 2 have intrinsic meanings. We're putting additional meaning to those particular values. Connascence of meaning. Not a good thing, because again, that's an arbitrary choice and could change easily. What we really like to do is put those variables in a named constant, and then use that name both in the view and then in the controller where we process it. Again, notice what we did? We converted connascence of meaning to connascence of name. What rule is this? Don't use magic numbers. And don't use magic numbers follows naturally out of the rules of connascence and converting from a high connascence to a lower connascence. Okay, this is interesting. This is actually not connascence. Let's look at this again. There is a relationship between these 2 lines of code, between the 1 and the 2. There we go. My battery must be dying. Now, I can change that 1 to anything I want to, and it doesn't matter, except if I change them both to the same thing. So here is some things that are different and need to remain different. This is called contranascence. And you find this actually quite a bit. Suppose I wrote an XML library that had a class called Node, and you wrote a graphing library that had a class called Node. And you're going to have a name conflict. You need to put them in your own namespace to prevent name collisions. Turns out there's a lot of nodes in Ruby, and they're all in their own namespace, and it doesn't collide. So this is how to avoid contranascence, is to put them in separate spaces, in this case namespaces. Here we have a method toNode, which we learned earlier today. Putting this on the basic object is not a good design example. Kent Beck told us that. But if you do, you have a collision between 2 names. You have contranascence going on, and there's no good way in Ruby to prevent this other than to not do it. Hopefully in Ruby 2, we're going to get selector namespaces that will address some of that. One last connascence I want to talk about, and I can see my time is almost up anyway, so let's go through this quickly. Here we have a routine that says, that calculates a checksum for a string. And it adds that check digit to the end of the string. Then we have a method called check that checks to see if the correct check digit is there or not. The code for that looks like this. And there is a connascence between these two things. And this is a connascence of algorithm. If I change the way the checksum is calculated, I have to change two separate locations to do that. Not a good thing. How do I prevent that? By refactoring it so that we have a common method called checksum that calculates the checksum for me, and I can use it in both the add check digit and the check question mark method. And again, what we've done is take a high level of connascence of algorithm and convert it to a connascence of name, a lower level of connascence. So we see that a lot. This is also called the dry principle. Represent knowledge in one authoritative place. Okay, so in quick summary, there's lots of connascences that I didn't have time to cover today. We covered most of the static kinds of connascences. There's a number of dynamic connascences that you can deal with. Connascence of execution means that you have to execute things in a particular order. Connascence of timing is what gives rise to race conditions in multi-threaded programming. So connascence of identity. How many people have felt the hurt from the lack of an identity map in Rails? Connascence of identity is why you feel that pain when you run into that. And a couple rules to live by. Like I say, I'm kind of in the stage of the scientist right now where I haven't put all this together that I can explain all the design principles we talked about today. But I'm feeling that connascence is one of those low-level principles that if you understand what's going on in terms of connascence, it's going to give rise to a good understanding of the law of Demeter, the dry principle, and these other principles that we talk about all the time. So here's some references that you can use. This whole talk is up on GitHub under my name. And there's a link right there. And I think, yes, the oatmeal rocket. I love that. And this says I am just out of time. So I'll be out in the hall for questions if you want to talk to me later. Thank you so much.